In the last lecture, we talked about the greenhouse effect in Venus, Mars and Earth, and we showed that Venus has a strong greenhouse effect because of the very thick atmosphere and a lot of CO2, while Mars has almost no greenhouse effect because there is no atmosphere, and Earth is in between. Okay. On Earth, we showed that water vapor has the strongest greenhouse effect. Next is carbon dioxide and other minor gases. And we argued that although water vapor is the dominant greenhouse gas on Earth, we have no control over amount of water vapor on Earth because it depends on temperature. And the temperature of the Earth is controlled by carbon dioxide. So, carbon dioxide is the main driver and water vapor responds to that drive. Okay. Now, what people generally do to study the Earth's mean climate is write a simple energy balance. Left hand side is the energy absorbed from the sun, which is the first is the S/4 radiation arriving per unit surface area of the Earth. This is the energy reflected in all direction, all wavelength, and one is this is energy absorbed by the Earth atmosphere system. Okay, and the right hand side is the energy going to space. Now, the simple way of writing is to write down what is emitted by the Earth's surface, assuming it is a black body, and F is a fraction which reaches space. Now, this fraction depends upon greenhouse effect, and so this number is to be calculated. Now, many papers and books call F as the effective emissivity, which I think is very misleading, because as you will see as I develop this simple model, F does not just depend on the emissivity of the atmosphere, it depends on many other things. Okay. Although you will find many people use this approach for simplicity, to me it causes a confusion, because we will show later on that F depends not only on the emissivity of the atmosphere, also on Earth's albedo, which is in the solar region, and Earth's absorptivity to solar radiation. Okay. So, remember that this is not the right model. Okay. Now, based on the measurement made by satellite, we know that the S value is around 1364. We know that we saw the variation of albedo with different months. The mean value over the year is around 0.3, and if the parameter F was 1, that is no atmosphere, then of course you can from this equation you will get F is 1 will get 255 Kelvin as the result of this equation, and that is of course not true. What we know is 288. So, we must conclude that F is not equal to 1. Now, the reason why F is not equal to 1 is because the atmosphere is almost transparent. This absorptivity of the atmosphere is almost transparent to the solar region, but almost opaque, absorptivity 100% in this region, except for a small region around 10 microns where there is a minor window, okay, where it is transparent. Most of the places there is completely opaque. That is what makes atmosphere of the Earth very unique. Now, let us write a simple model of the Earth's atmosphere as before the radiation coming in, the sun per unit surface area, and rho is the albedo. So, this much is reflected and this much is absorbed, and if you neglect the atmospheric solar absorption right now, we will add it later, this 1 minus this will appear here. Okay. Whatever is not reflected, it comes to the surface, and the surface of the Earth emits like a black body, our assumption, and we treat atmosphere as a black body, which is not right, but we will start with that assumption, and we assume that it reflects equally in both directions, which is again not very accurate, but it is a good starting point for a simple model. So, when you do all this, at the top the radiation absorbed in the sun has to be equal to radiation emitted to space by the atmosphere, because atmosphere is a black body. At the surface, we have radiation reaching the surface, and this is the quantity which is emitted downward by the atmosphere to the surface. So, these are two terms of radiation coming into the surface, one coming after reflection by the atmosphere to the surface, and the other is by the atmosphere to the surface, this term, okay, and that should be equal to radiation emitted by the surface. Okay. Remember, we are neglecting energy transfer from the surface of the atmosphere by evaporation and turbulent transfer, which is an approximation we are making, which we will take care of later. Now, if you eliminate in the previous equation Ta, this term can be substituted by this term, you will get twice this term. You will get a simple result that Tg to the power of 4 times sigma is as before twice 1 minus rho. Okay. And for the given observed value of albedo of 0.3, you will get 303 Kelvin. So, this very simple model we are starting with is better than 255, but it is too high, because we know that the surface temperature of the earth is around 288, this is saying 303. So, we are off by around 15 degrees Kelvin, and that is because we are doing two mistakes. One, we have neglected the absorption of solar radiation by the atmosphere, and also assumed atmosphere to be a black body. So, we will now have to relax this assumption to have a better result. So, next model I do is you account for the absorption of solar radiation by the atmosphere. I use capital A. I could have used alpha, but I use capital A to denote atmospheric absorption of solar radiation. So, otherwise the equations are similar to what we wrote last time, except that the Earth's surface will now receive less radiation, because amount A is absorbed from the incoming radiation. Okay. So, again you can eliminate Ta and you will get this result. Okay. Now, if you take the calculated absorptivity of solar radiation in the Earth's atmosphere as 0.2, which can be calculated from some models, and you assume 0.3 is a measured albedo, you will get 291.5, which is quite good. So, now with inclusion of absorption by the Earth's atmosphere of the sun's radiation, we are getting 291.5, which is only 3.5 Kelvin larger than the measured global mean temperature. So, we are getting closer to the observation, and remember, this model has only three values: incoming solar radiation S, percentage radiation absorbed by the atmosphere, and the albedo of the earth. Just by three measurements, we are coming to a number within 3.5 Kelvin, but we are not happy, we want to do better. So, we want to put one more thing, we want to relax the assumption that atmosphere is totally opaque to Earth's radiation, which it is not, because some radiation escapes through the so called atmospheric window, this region at 10 micron, something escapes around 5%. So, we want to account for that. So, we build a better model. This model now has radiation coming in from the sun, reflected by the Earth atmosphere system, and we account for the emission by the atmosphere, which is not a black body, emissivity of the atmosphere. Okay. And then we solve for it. I am sorry, you should have accounted for here the absorption of solar radiation. I will correct that, and then we get the following equations. In this equation, at the top is the radiation that is absorbed from the sun at the top of the atmosphere. The right hand side is the radiation emitted by atmosphere to space. The third term is a new term, radiation emitted by the surface, which is transmitted through the atmosphere. Whatever the atmosphere does not absorb is transmitted, and 1 epsilon is the transmission. Okay. So, this is a new term which was not there earlier, and this term was already there, and this term is the emission downwards to the surface, and this is the surface emission. Okay. So, now we have S, epsilon, A and rho, 4 parameters. Okay. And again you can eliminate T A between these two equations and we get this result. Okay. So, this result is much better than last, because this result you put the incoming radiation, albedo measured, absorptivity calculated and emissivity estimated from some models, you get exactly 288. Okay. So, this is partly lucky because approximations have been made and they are not affecting us too much. So, what I want you to appreciate is that we are able to get the global mean measured temperature of the earth with a very simple model without using any computer based on just 4 parameters, and these 4 parameters are incoming solar radiation, Earth's albedo measured by satellites, the absorption of the Earth's radiation by atmosphere and the surface calculated, and emissivity of the atmosphere calculated from radiative transfer models, okay, based on composition of the Earth's surface. So, by just these 4 parameters we are getting 288. So, I wanted to remove this model because this is the simplest model which, without doing complicated computer simulations, we are able to explain the global mean temperature. Okay. But this model has limitations. It has neglected the transfer of heat from the surface to the atmosphere by evaporation. Water evaporates on the surface of the earth and condenses in the atmosphere, transfer of the heat is very important. Then of course, winds remove the heat from the earth's surface and put it in the atmosphere, that is also neglected, because we have done only radiative transfer balance, we are not taking into account other processes. Okay. These assumptions can be relaxed, you can easily, I will give you an exercise to relax assumption to put in these terms. And the other important neglect in this model is, we are assuming that the Earth's atmosphere emits equally up and down, because we assume atmosphere is isothermal, but this is not true. The atmosphere is not isothermal because the temperature of the atmosphere decreases with height. We all know that the temperature at the sea level is the highest at the surface. As you go up a mountain like Mount Everest, it is much colder, because the temperature of the earth varies from the surface to the top of the atmosphere, because most of the radiation is absorbed by the surface, it heats up, and that heat is transferred to the atmosphere. So, atmosphere is always lower than the earth's surface, and as you go higher and higher, it becomes lower and lower. Okay. So, that we are not accounted for, that is a serious approximation, but these two approximations, the neglect of evaporation and sensible heat flux, and the fact that atmosphere is not isothermal, they have approximately cancelled out, 2 errors cancelled out. So, we are lucky, we are getting a simple model. So, although we are very happy, we must realize we are lucky, but we can easily put these 2 in. But the only trouble is, I can't give you a nice analytical solution. You will do an exercise which will include these 2 terms. You will then have to do some numerical calculation to get the answer. You won't get this simple result. Okay. Now, again let me summarize this. the simple result we got with these two parameters, all are measured parameters, which gives the right answer. But if there was no cloud, cloud contributes to the albedo of the Earth. If cloud is not there, albedo will drop down to 0.15, then the temperature will go up to 305, that is, it will increase by 17 degrees centigrade. Okay? So, I want you to realize how sensitive the Earth atmosphere is to clouds, because we will later in the course will discuss clouds, which is very important in controlling Earth's climate. Okay? And you can see that if you go from the present cloud level in the atmosphere, which gives albedo of 0.3, to an atmosphere with no clouds where albedo is 0.15, temperature would increase by 17 degrees centigrade. So, what this says is the presence of clouds in the atmosphere today is cooling the Earth by a substantial margin. Okay? So, if these clouds change due to climate change created by human beings, we are in trouble. Now, if the clouds increase, that will somewhat counterbalance the heating caused by greenhouse effect of CO2, but if the clouds decrease, the Earth will get warmer and will add to greenhouse effect. We still do not know what is the direction in which clouds will change, and that is a major uncertainty in core climate models. If we look at many climate models which are being run today, which we will discuss later in the course, some models say clouds will go up, some models say clouds will go down, and we are not sure which way the reality is, because clouds are very complex. There is not one cloud, there are many types of clouds, and different clouds have different impact on Earth's climate. So, this is a fact you have to remember, that this simple model hides that fact, because we are using the assumed albedo, but albedo will vary according to clouds, and that will alter the Earth's climate. So, remember that this simple model has been constructed based on observed values, so it gets the right answer, but if we do not know how clouds will change in the future, we do not know how the Earth's temperature will change. And again, reminding you that if there is no atmosphere, A is 0, epsilon is 0, we will get 255 Kelvin. But if we only neglect solar absorption, which we did earlier today, you will get 303 Kelvin. So, we cover all the aspects of the simple model in one slide. So, please go through it carefully to understand how different parameters control Earth's climate. Now, so note that this simple model, which was proposed by Professor K.N. Liu of the University of Utah, and taken this model from his book, which I mentioned in the first lecture, is able to predict correctly global mean temperature based on just 4 parameters. They are the incoming radiation, solar absorptivity, and infrared emissivity of the atmosphere. But remember, these parameters depends on amount and type of clouds, infrared properties of minor gases, ice cover and vegetation. Okay. So, by specifying these numbers, we are somewhat hiding the complexity of the Earth, but this is the beginning of the course. I want you to have in your mind a very simple model to have an understanding of the Earth's global mean climate. But as we go along, we will highlight the complexity of the Earth's climate, but to be able to explain to others, this model is very useful, okay, to tell how each of these 4 parameters alter Earth's climate. I am saying this because about 30 years ago, when first the global warming issue was widely debated, many people said sun's radiation will affect climate more than the human beings. Now, sun's radiation of course is very important for Earth's climate, but at that time adequate data was not there to demonstrate how the incoming radiation is changing. today we have about 60 years of accurate data of the incoming radiation S as measured by satellite, and they show that in the last 60 years the incoming radiation, the annual mean, varies by hardly 0.1%, that is all. Okay. So, it does not vary much. So, those who thought that you can explain the warming of 1 to 1.5 degrees in the last 150 years by varying sun's radiation, we can show that they are wrong now, because we have measured S value accurately in the last 60 years. So, to understand all this, you take this formula and try to calculate the sensitivity of this temperature to variation of these parameters. Okay. Because this is an analytical expression, we can differentiate using calculus. The first thing I will do is ask how does the surface temperature vary with the incoming radiation. So, differentiate the above equation with S, very simple because S is linearly dependent, and then do a little manipulation, combine these two, you get a very simple result that 1 over Tg delta Tg delta S is 1 by 4S, or delta Tg by Tg is delta S by 4S. Okay. That is, very simply put, if the incoming radiation changes by 1%, the impact on temperature is 1/4 of a percent, that is all. Okay. So, 1% is delta S by S, then delta T by T is 1/4 of a percent, which is not small, but satellite data shows that the Earth's incoming radiation in the last 60 years has changed at most by 0.1%. Okay. So, its impact on Earth's temperature is 1/4 of 0.1%, that will be about 0.1, 0.2 degree Kelvin. So, that we cannot explain the temperature change in the last 60 years by invoking changes in sun's radiation. Okay. In the past, a lot of changes may have occurred, we will talk about it later, but in the last 100 years sun's radiation has not changed by more than 0.1% during the solar cycle of 11 years cycle that we see. Now, let us look at other parameters, how they depend on how the temperature depends. One is the solar absorptivity. Solar absorptivity can change due to changes in atmospheric composition. You can see that a 1% change in absorptivity causes a 0.6 Kelvin cooling. So, for example, if we had a lot of soot in the atmosphere or any other gas that absorbs solar radiation, it will cool the Earth by around 0.6 Kelvin. If you change the albedo of the Earth either through clouds or through changes in ice cover and snow cover, let us say by 1%, it will cause much larger cooling, 1.2 degree cooling. Okay. And finally, if we change the emissivity of the atmosphere by changing composition of CO2 or methane, 1% change in emissivity causes 0.75 Kelvin. So, the major message I want you to see is a 1% change in any of these 4 parameters causes around a degree Kelvin change in temperature. 2 of them are warming, that is incoming radiation and emissivity. The other 2 are cooling, absorptivity and reflectivity. Okay. So, we have to keep this in mind in talking about the future climate change. Now, you must remember that right now we are changing climate by merely changing the emissivity. Okay. But once the emissivity changes of the atmosphere, temperature will change. When temperature changes, it will change both the absorptivity and reflectivity of the atmosphere, because ice will melt, and we know that water is a much more stronger absorber of solar radiation than ice. So, change in temperature will cause change in these 2 parameters. So, these partial derivatives are not very useful. When you take a partial derivative in calculus, you assume all the other parameters are constant, which is not true in the case of Earth system. If you change one parameter like S and the temperature changes, all the other parameters will also change. This is called feedback. That is, once the temperature of the Earth changes due to change in one parameter, automatically other parameters change and they change temperature again. So, this is a very important topic which I will cover next, how the change in temperature of the Earth due to one change like the incoming radiation will change the other parameters A, epsilon and albedo and will cause further change. So, one chain triggers a chain reaction. This chain reaction is called feedback, and this feedback word comes from control theory. Okay? And a positive feedback means if you trigger a change and something in the system changes and adds to the change a positive value, temperature will increase further. That is called positive feedback, while the change you triggered causes something to change so that the Earth cools, it is called a negative feedback. So, as far as we are concerned, negative feedback is good. It will make the system more stable, and positive feedback is bad because it will add to the change. Okay? But the English language, the word positive is usually considered to be good, but in the context of this subject, remember, positive feedback is bad, negative feedback is good. Keep that in mind. Okay? Now, the simple model shows that a 1% increase in the value of S will increase the global temperature by around 0.72 degrees Kelvin. The data from satellites have shown that changes by less than 0.1% occur during the 11-year solar cycle that we have observed over the last 60 years, and the increase in global temperature of 1.5 degrees centigrade during the last 170 years cannot be attributed to changes in incoming radiation. This is a very important conclusion, because some astronomers thought that the warming and cooling of the Earth is primarily due to changes in sun's input. That may have been true in the past, millions of years ago, but in the last 100 years, sun has not been the major contributor to the global climate change of 1 degree centigrade. Now, I want to repeat this point, that many books talk about a simple model using F as a parameter and assuming F to be constant, but we have shown in this simple Lewis model that F is not a constant, depends on not only emissivity, but also the solar absorptivity and the albedo, and so cannot be assumed to be a number which depends only on infrared properties of the Earth's atmosphere. This is very important conclusion from the simple model I have presented. Keep that in mind in the future discussion. Okay. Now, I want to remind you that the simple models assume that Earth atmosphere is one temperature. This is not true. Observations show that the atmospheric temperature decreases by 6.5 Kelvin per kilometer, and this model still works because there is some cancellation of two quantities we did not include, but you cannot use the simple model for Venus. Venus has a much thicker atmosphere than Earth, so the temperature is changing much more. Venus surface temperature is 700 Kelvin, at around 50 kilometers is 200 Kelvin. So, the change is so large that you cannot treat it as a isothermal atmosphere. So, we cannot use Lewis model for Venus. I will talk about what model we need to develop for Venus, which is totally different from what we did for Earth, because Venus is more complicated. Okay. So, for Venus we need a separate model, because this model is meant for Earth like atmosphere. It will work for Mars, which has almost no atmosphere, for Earth and other planets in the universe whose atmosphere is not very thick. Okay. But for Venus it will fail. For Venus we have developed a different model. So, keep that in mind as we go along this course. Okay. And if you want to then use model for Venus, then you use many layers. We use a one layer model, you can use an n layer model. Okay. And for each layer you can do energy budget. This gets pretty complicated, and so you need a computer, you cannot do hand calculations. Okay. So, this will be given as an exercise to you to do, and you will see that it gets pretty complicated. And so, it has been used in complex climate models. They divide the Earth's atmosphere into 100 layers, and they use isothermal assumption in each layer. That is okay, but you cannot write down a simple formula. You have to run a computer model many times. Okay. With that, I conclude this lecture, and we will continue to discuss these models with other applications. Thank you.